Hello, welcome back to short lectures in physics. The topic to be discussed in this session is vertical motion under gravity. The vertical motion of a body, when it is projected up, it will go linearly to some height and then it falls back. In both directions, it is it is under the influence of the gravitational force, that is due to Earth's gravitational attraction. So, because it is traveling in the linear path while going up and then coming down, the equations for linear motion can conveniently be used for analyzing the body motion in vertical direction. Let us recollect the equations of linear motion. If u is the initial velocity, a is the acceleration, then v velocity in time t for a body in linear motion that is moving with uniform uh, acceleration is given by v is equal to u plus at. Similarly, distance travelled by it in the time for the given conditions is s is equal to ut plus half at square. And the equation that relates distance, final velocity, initial velocity and acceleration terms is v square minus u square is equal to 2as. S is the distance travelled. And distance travelled in the nth second of travel is Sn is equal to u plus a by 2 into 2n minus 1. A is the So these equations can be conveniently used for studying the vertical motion of the bodies under gravity. To understand the vertical motion under gravity, bodies moving vertically upwards with some initial velocity of projection, they rise to some height and then falls freely to the ground under the influence of the g force, that is 9.8 meters per second square, that is the acceleration due to gravitation force of the earth. Here we can note that while going up against the g force, the velocity of the body decreases every second by 9.8 meters per second till it reaches a maximum height where the velocity of the body becomes 0. From there, it drops down to ground as a freely falling body and its velocity increases by 9.8 meters per second every second. So while going up, the velocity decreases by 9.8 meters per second, and while dropping down, the velocity increases by 9.8 meters per second, because both cases the acceleration due to gravity is influencing the motion. Now coming to the equations of motion for the freely falling body, because its motion is also similar to bodies moving with uniform acceleration. Here the acceleration is because of the gravity. So its equations can be same as those used for linear motion with uniform acceleration as already. Only thing is the distance or displacement has to be replaced with the height term, and the acceleration term should be replaced with the g gravitational force. That's all. In general, the height h is given by average velocity, that is v plus u by 2 into the time of travel. So making use of these things, we can obtain the equations of a freely falling body as v is equal to u plus gt, h height is equal to ut plus half gt square. See here a is replaced by g because it is falling down, the gravitation force is plus, and v square minus u square is equal to 2gh, and nth second height travel h nth is given by u plus g by 2 into 2n minus 1. Similarly, for an upward projected body, when body is projected up, v is equal to u minus gt, h is equal to ut minus half gt square, v square minus u square is equal to minus 2gh, h nth is given by u minus half g into 2n minus 1. Here g is used with a negative term. Few important points you can remember while dealing with the vertical body motions. The body is taking some time to rise to a certain height and then some time to come back to the ground. it may be noted that the time of ascent, that is time taken for the body to go from ground to maximum height, is same as time of descent, that is the time taken for the body for dropping down to ground from the maximum height. So time of ascent is equal to time of descent. If a body is projected up and then received back in a time capital T, then the time taken for it to reach you will be half the time, T by 2. That is the important point here. And it may also be noted that velocity of the body when it touches the ground, that means with some velocity it has been projected up and then it comes back to the ground. It reaches to maximum height where velocity is 0. Then again velocity increases as it returns to ground. So the velocity when it touches the ground is same as the velocity with which it has been projected up. That is, at any point in the trajectory of the vertical body motion, the velocities remain same. That is the gist of this. So the velocity of projection is same as the velocity with which the body returns to the ground. That points P and here one thing you remember that though we are showing two lines for indicating the figure, two lines we are using to indicate the ascent travel and the descent travel. But actually the both will be in the same line because the body goes up and falls down in the same line. Only for convenience we are showing as two tracks in the figure. So at any intermediate position like points P and Q on the upgoing journey and then return journey of the vertically projected body, the velocity is same as Vx. That means from ground at a distance of x, the velocity if it is Vx, then the velocity at h minus x from the top position is also Vx. That is points P and Q will have at the same height from the ground or having same velocity. This is the important point we have to remember. And then suppose a body is projected up, the velocity u, initial velocity u, takes t seconds to reach a height h small t, then falls back in another t. As you told, time of ascent is equal to time of descent. So it takes same time t for going up and coming down. Then the height can be taken as half gt square using the freely falling body motion equation. That is, as if it is falling freely from the maximum height, you can calculate because initial velocity is 0, you will get ut plus half gt square. So u will be 0, so you will get half gt square. If t is known, the height can be calculated from, even if the time of ascent is known, then height can be calculated from the falling condition. That is, here you note that the height is independent of mass of nowhere we are dealing with mass. Hence, bodies of different masses, when they are projected with the same initial velocity, they reach same height respect of their masses because they are independent of the mass. This is another point we have to remember. And the velocity of projection, because height we determine from the return body equation. Now u, velocity of projection, can also be determined from v is equal to u minus gt for the upgoing body conditions, where v is equal to 0, so u becomes gt, t is already known, g is known, so u can be calculated. So both conveniently, whatever equation is useful for solving our problem can be replaced. And if distance traveled in t plus 1, that means t seconds is the time of ascent, suppose time of descent also. So if the distance traveled in plus 1 second, that is after the t seconds, plus 1 second is required, then it is nothing but the distance traveled by the freely falling body in its first second, because first t seconds goes for time of ascent and the 1 second is the first second of its return journey condition. So you can take that as the distance traveled by the freely falling body in its first second of travel to ground after reaching the maximum height in t seconds. So that's ht plus 1 is equal to half g into 1 square, that is half g. Here we are not using h nth second formula because Already we reached the maximum height in t seconds. So the next 1 second is the first second of the falling condition. And its velocity after t plus 1 second also similarly you can calculate from the freely falling body condition. And you can see that the velocity after t plus 1 second is v is equal to g into 1, that is g meters per second. And every 1 second we said the velocity of the upgoing body decreases. So if it is projected with 4 times g velocity, then first second it will become 3g when going up, and second 2g, and then becomes 1g, and finally at the maximum g 0. Similarly, the falling body, first second it will be g, second it will be 2g, third second it will be 3g, and fourth second it will be 4g, with which the velocity, with which is the velocity with which it has been projected up. So every second the velocity changes by g value. Now let us see some numericals so that we can understand how these discussions are useful in solving numericals. A ball is thrown vertically upwards, reaches a maximum height in t seconds. Then the total time from the time of projection to reach the point at half its maximum height, means it went to the maximum height, and then while returning, while falling down, half the height it has to reach. So the time in t seconds for that travel is required again. So for upward travel of the ball, the height is given by v square minus u square by minus 2g, because minus 2g is because it is going upward. So it becomes, because v is 0, it becomes u square by 2g. But v is equal to, v minus u is equal to minus gt. V is 0, so u becomes gt, that thus h becomes half gt square, because t is known, t is the time for it to reach the maximum. So while falling down, let the ball takes t1 seconds to reach half the height, because in return journey it has to travel through half height. So its time will be t1 seconds. So that if you apply the distance formula, h by 2 is equal to ut plus half gt square. So h will become h by 2 half the height, ut1, u is 0 initially because it is falling from maximum height, plus half gt1 square. So u being 0, that becomes half gt1 square. So, but h is equal to half gt square already. So, gt square by 4 is equal to half gt1 square. Thus, t1 becomes t by root 2, 1 by root 2 times of the t. So, the total time taken the ball to reach maximum height after its projection is t plus t by root 2 seconds. It depends on the value of the t. Now, a body projected vertically up crosses a point twice. It is when projected, if somebody is watching from a floor, balcony, so he can see while it is going up and then while it is coming down. So similar situation. A body projected up vertically crosses a point twice in its journey at a height h, just after t1 and t2 seconds. Then the maximum height reached by the body you have to find out. Note that the time to reach maximum height from point at, at a height h, because we are seeing from the height h, will be same as the time of reaching the same point again. Whether it is ground or observation point, the time of while going up is time of ascent and time of descent are same in reaching the maximum height. So in the present case, this time will become half the t2 minus t1. T2 is the time for the body to reach the maximum height and then come back to the point to the same height again. So t2 minus t1 is the time difference. Then half of that will be the t2 minus t1 means t2 is the time seen second time, t1 is the time seen, the body seen in the first time. So t2 minus t1 is the time taken for the body to reach the height above the observation point and then return back to the observation point. So half of that will be time of ascent or time of descent. So t1 is the time to reach the height h while going up. Thus, the time taken by the ball to reach maximum height t will be t1 plus half of t2 minus t1. T1 is the time for the body from the ground to reach the observation point, and half t2 minus t1 is the time taken for the body to go to the maximum height from the observation point alone. So the total time of ascent from the ground will become t is equal to t1 plus half of t2 minus t1, that is equal to half t1 plus t2. Thus maximum height is equal to half gt square, considering the freely falling body equation. So that is equal to 1 by 8 g t1 plus t2 whole square. G is known. If t1 t2 values are known, you can calculate the maximum height the body has reached. Now these under interesting phenomena. Water drops fall from a tap on the floor 5 meters below. The tap is at a height of 5 meters, and water is droplets are dropping at a regular frequency, regular time, intervals of time. The conditions given are: the first drop strikes the floor, first drop starts and then comes and touches the ground. By the time the first one reaches the ground, the fifth drop is ready to fall. So then the height at which the third drop will be from the ground at the instant when the first drop strikes the ground. That means when the first drop strikes the ground, fifth drop is already at the top tap head. So in between second drop, third drop, fourth drop as shown in the figure, in between three more drops are traveling towards the ground. So the third drop position is in the middle. So you can calculate the time for the first drop to travel through 5 meters. Then we will be able to calculate the third drop position. So the time taken by the drop to fall through height h is equal to half g square because it is freely falling. So t becomes 1 second. This 1 second is distributed into 4 intervals because between the time interval is between first and second, second and third, third and fourth, fourth and fifth. There are 4 intervals of time. So 1 second is divided into 4 parts, that is 0.25 seconds as shown in the figure. When the first drop strikes the ground, the third drop is in the middle position. That means from the ground, it takes for the third drop to reach the ground, it takes time 0.25 plus 0.25, that is 0.5 seconds. So the height covered by the third drop h is equal to half gt square, that is equal to half into 10 into 0.5 square. So 1.25 meters is the position of the third drop when the first drop touches the ground. The falling body covers an intermediate distance, s, in 2 seconds. That means it is traveling, but in between it travels a distance in 2 seconds, which is equal to the distance covered in the next 1 second. That means for t seconds it is there, t plus 1 seconds it is the another one. So when it traveled through some distance in 2 seconds, in the third second it travels through the same distance. If g is 10 meters per second, then the distance s is. If u is the initial velocity of the body at the time of the collision, distance covered in 2 seconds of trial is, because it is a freely falling body, we can use the u is equal to 0. So x2, distance traveled in 2 seconds of time, is equal to x2 is s is equal to ut plus object, that is 2u plus 20. U is not known. 2u is the velocity with which it is presented. So 2u plus 20 meters. And similarly, distance covered in the 3 seconds of time is 3u plus 45. So distance covered in third second, x3 is equal to x minus s. Total 3 seconds minus 2 seconds distance. That is u plus 25 meters. So given that the distance covered in third second is equal to that covered in 2 seconds. Thus 2u plus 20 is equal to u plus 25. That is u is equal to 5 meters per second. Thus s is equal to 2 into 5 plus 20, that is 30 meters. Now, another interesting. A ball is thrown vertically upwards with a speed of 10 meters per second from a top of a tower, from a balcony or top of a tower, which is at 200 meters height. Same time, another ball is thrown vertically downwards with the same speed, that is 10 meters per second speed only. Another ball is thrown to the ground from the top of the tower. One is up, one is down. Velocity of projections are same in both cases. Then the time difference between them in reaching the ground, assume g is equal to 10 meters per second. That means the body which is projected up from the tower has to travel some more distance up and then come back to the tower height and then reach the ground. Whereas the one which is projected directly down can straightway travel through the height of the tower and reach the ground. So the difference you can remember here is at any point intermediate position in the upgoing and the down travel trajectories, the velocities are same. So if you consider that point at the top of the tower, the velocity with which it is projected up when it is coming down, its velocity becomes again same. That is, if it is u with which it is projected, that's 10 meters per second, it goes up first of all. When it goes up, it reaches maximum height, velocity becomes 0 and then drops down. And when it reaches the top of the tower, that is observation point again, it velocity again 10 meters per second. That means the first body, though it is going up and coming down, it is similar to the condition of the second body, which is projected downwards with 10 meters per second vertically down. So the first body also, though it went up and then come down, it is also having same velocity as 10 meters per second at the top of the tower, while and going back to the ground, falling onto the ground. So the conditions of the body 1 and then body 2, both balls conditions are same as far as the downward journey is concerned from the top of the tower. Only difference is the first ball went to some height and then returned back to the cover. So if you calculate that time, then that will be the time difference. Same question. So height reached by the first ball above the tower is equal to, considering the freely falling condition, h is equal to u square by 2g, that is 100 by 20, that is equal to 5 meters. And time taken to reach this 5 meters above the tower is equal to 2h by g under root. So you will get 1 second. So the time taken by to return to the top of the tower is also, because time of ascent and time of descent are same. So it will become t2 is equal to t1 is equal to 1 second. Thus, the time difference between the two balls in reaching is equal to sum of this time of ascent and time of descent becomes 2 seconds. That's how the time difference becomes t is equal to t1 plus t2, that is 1 plus 1, 2 seconds. A stone thrown up with a velocity of 4.9 meters per second from a bridge in vertical upward direction falls down in water after 2 seconds. Then these are also similar to the earlier numerical. The time taken by the stone to reach some height above the bridge, because from bridge he has thrown up. So t becomes 4.9 by 9.5 seconds, because v is equal to 0 and g is equal to u minus gt. And time taken by to return back to the bridge is also twice of that. So it went up and then come back to the bridge takes 1 second. Given that time taken by the stone to fall in water is 2 seconds. So the difference, that's 2 seconds minus 1 second, that 1 second is the time taken by the stone to reach water from the bridge height in its return journey. So the velocity of the stone with which it drops down into water from bridge while falling is same as that with which it has been projected up against same condition. So height of the bridge becomes h is equal to 4.9 into 1 plus half into 9.8 into 1 square, that's 9.8 meters. A ball thrown vertically upward from the ground passes the top of a tower at t is equal to 3 seconds. If it reaches the maximum height in 2 seconds later, height of the tower, assume g is equal to time. Time of ascent is equal to, because it traveled from the ground to the top of a tower in 3 seconds and then it continued further 2 seconds to reach the maximum. So the total time of ascent is equal to 2 plus 3, 5 seconds, which is also equal to the time of descent. So maximum height reached by the ball is equal to, considering the freely falling body, half gt t descent square, that is equal to 125 meters. So height covered by the ball in 2 seconds of travel after reaching the top of the tower is equal to that covered by freely falling body from its maximum height in first 2 seconds. So that if that is x, half gt square, it's 20 meters. So the height of the tower is equal to total height minus total height is 125 meters we got. In that, the height above the tower, bridge or tower can be removed, so that 125 minus 20 is 105 meters is the height of the tower. A ball is left freely from a height. So it traveled for 6 seconds and then crashed through a horizontal glass plate. It has fallen on a glass plate where its velocity it lost its velocity by two-thirds. That is, one-third is the remaining velocity. If it then reaches the ground in 2 seconds, find the height of the plate above the ground. So velocity of the ball at the time of crashing the glass plate is equal to, because it is freely falling, v is equal to u plus gt. So gt, u being 0, gt, that is 58.8 meters per second, which becomes one-third because two-third is lost. So velocity of the ball after crashing through the glass plate is one-third of v, that is 19.6 meters per second. So height of the glass plate is equal to h is equal to ut plus half gt square, that is 19.6 into 2 plus half into g into t square 2 square, that is 58.8 meters. Let a ball dropped from a height of 12 meters from its rest position, height is 12 meters, freely falling again. It loses 25% of its instead of velocity loss is telling kinetic energy loss on striking the ground. Then the height to which it bounces back. After falling on the ground, it lost some energy because velocity will be there. The velocity increases as it falls under the influence of gravity. So with that energy, after bouncing, how much height it reaches, we have to find it. So the potential energy of the ball at 12 meters height is at mgh, that is 12 mg. Loss in kinetic and that potential energy will be converted into kinetic energy as it touches the ground. So the potential energy at maximum position is nothing but is equal to the kinetic energy at the ground. So loss in kinetic energy of the ball in hitting the ground is equal to 25% is lost. So 25 by 100 into 12 mg. So the remaining energy, the energy with which it bounces back is 12 mg minus 3 mg, that is 9 mg. And this is the energy possessed by the ball. Same kinetic energy will be there, will be present in the body as potential energy at the height h after bouncing from the ground. So this is the energy possessed by the ball when it hits the ground and also at a height h after bouncing from the ground. So potential total energy of the ball at height is equal to mgh, that is 9 mg is equal to mgh, so h becomes 9 meters wide. Hope this gives some insight into the vertical motion of the body under the influence of gravity. Hope you enjoyed the video. See you in the next topic of discussion. Till then, bye.